Good evening, everyone. Welcome to the webinar where we're going to talk about leveraging LangChain frameworks. So this is a modular system that helps orchestrate large language models with external data sources like databases and documents in order to produce intelligent answers. Now let's walk through each section of the framework in detail. First comes your query construction. This is where the user's natural language question gets translated into a structured query. So first we have relational databases. For example, SQL databases basically uses text to SQL. It converts natural language into SQL queries, possibly with tools like pgvector. Then we have graph databases. For example, Neo4j. It uses text to cipher, converts natural language into cipher queries to transverse graph databases. Then we have vector databases, for example, FAISS, Pinecone, so many examples, right? It uses self-query retriever. Automatically, it extracts the metadata, filters from the question to retrieve the relevant documents. Then comes your query translation. Once a question is constructed, it may need to be translated into a more effective form for the retrieval. Here, the techniques used are multi-query, RAG fusion, decomposition, step back, hide. Multi-query, it will generate multiple variants of a query. RAG fusion will fuse the output from retrieval-augmented generation. Decomposition, it will break the complex questions into simpler parts. Step back HYDE, hypothetical document embeddings, will retrieve the better context. Then comes your routing. So this routes the question to the appropriate source, like your database or vector store. There could be logical routing, which is LLM chooses the best source, right? For example, relational database versus vector database. Or semantic routing, where it embeds the question and matches it with the most relevant prompt. Then comes indexing altogether. Indexing is the process of organizing the documents for efficient retrieval. We have chunk optimization, multi-representation indexing, specialized embeddings, and hierarchical indexing. Let's try to understand each one of them. So chunk optimization will split the text into meaningful chunks using characters, sentences, or semantic delimiters. Multi-representation indexing will store both full text and summaries for different kinds of use cases. Then we have specialized embeddings. This will use fine-tuned models like Colbert for specific domains. Then we have hierarchical indexing. This will use multi-level summarization like Raptor. So you can see here the initial document being split into clusters and then summarization. Raptor is basically a tree of document summarization at various abstraction levels. Hierarchical indexing is used for multi-level summarization for scalable document search. Okay. Then let's talk about retrieval, right? Once the question is routed and translated, relevant documents are being retrieved. So we have different methods to do this. We have ranking, refinement, active retrieval. Let's look into each one of those. Ranking basically will use methods like re-rank or rank GPT to sort documents by relevance. It will sort the documents according to the relevance. Okay. Then we have refinement. In refinement, we have something called a CRAG method, which will fine-tune your retrieved results. Then we have active retrieval. Active retrieval, CRAG can also re-retrieve the documents from new sources if at all the initial results are not relevant. So if something is not relevant at the refinement stage, re-retrieval will allow you to do that using CRAG. So re-retrieve and or retrieve from new data sources. If retrieved documents are not relevant, this will act on it. Okay. Now let's talk about generation altogether. Final step where the LLM uses retrieved content to generate an answer in the first place. So we can use self-rank here or RRR, that is re-ranking and re-retrieval. Self-rank uses generation quality to guide further retrieval. Whereas RRR, that is re-ranking, re-retrieval, informs if documents need to be re-ranked or we need to pull in new documents. So this is the flow summary. And you can see here, once the question is asked and the semantic routing is done, the query construction will be done at the next stage. You can either send it to graph databases or relational databases or vector storages. And then all the chunk of documents will be put into the retrieval part. Then you can see how it's generating the answers. And every generated answer is again going back as a feedback to the vector store, back to the vector store. This is how a LangChain framework works in the first place. Now let's see an example of one of the codes. Let me walk you through the example code. All right. So the first thing that we're doing here is installing all the necessary required libraries. Okay. LangChain library, which is basically a framework to build applications using LLMs. Then we have Hugging Face underscore hub. This will allow you to access to the models hosted on the Hugging Face website. Then LangChain underscore Hugging Face. This particular library, this is used where LangChain integration with Hugging Face interface endpoints. Then sentence transformers, embedding models, which are often used in the retrieval stage. Okay. Now, let's log in, right? So from Hugging Face Hub, we're importing a module called login. This will authenticate with Hugging Face using a personal access token. Then we have Hugging Face endpoint. So we're importing LangChain from LangChain underscore Hugging Face module. I'm importing a function called Hugging Face underscore endpoint. This Hugging Face endpoint will provide an interface for sending the prompts that are to be hosted on the LLM on the Hugging Face itself, right? Okay. Then we are giving the Hugging Face token here. Now, actually, this should not be exposed publicly. You can go to your Hugging Face module, Hugging Face website and generate an access token. I'll also briefly show you how that is done, right? How we are bringing this Hugging Face token in the first place. Okay. And then we log into the Hugging Face using this particular token. This will authenticate the session using the provided token here. Once we log in, you can access the private or the gated models or models that require authentication. So it's very important to log in, right? And then we are trying to define the model or set up the model. So repo underscore ID, here is where the path to the model on the Hugging Face Hub is given. In this case, we are using Mistral 7B instruct v.03. This is basically a fine-tuned LLM for instructions and for chat. LLM. Now, this object will allow you to send prompts and receive generated responses using LangChain's abstraction. So, this is where we are mentioning our parameters, right? Repo ID as the repo ID itself, and in the token, I'm allowing it to access this particular Hugging Face token. Okay. Now, to test the model, we're basically sending a test prompt. This sends the prompt to the model. Okay, dot invoke that we're using here, basically it's the method to query the model and get its output generated. And finally, these print statements will allow you to display the input prompt and the model's response. Okay, let's do one thing. Let's run this code now. So the first thing that I'll be doing is probably checking my runtime. So always set your runtime to GPU when you're running these kind of models. First thing, I will install these required libraries.
इनको आपका मैसेज आया हुआ है
Okay. So when we are installing these dependencies, so it's getting connected with the CUDA, GPU. Yeah. After we successfully install, we're going to import these libraries. Yeah. Once we successfully install all of this, we are importing the required libraries here. So from Hugging Face underscore hub, I'm importing the module login to be able to log into my Hugging Face token in the first place. Then from LangChain underscore Hugging Face, I'm importing the module Hugging Face endpoint. Okay, and here I've entered my token. So I'll show you how we generate the token in the first place, right? So I'll take you to the Hugging Face platform. Yeah. Once you basically successfully log in with your credentials, you can click on your username and here you have the option of access tokens. Now I have already generated an access token. You can do the same by clicking on create new token. You can name the token as anything. And once you do give a name to the token, you can just go at the bottom and maybe click on create token, right? That would help you generate a token in the first place. And you can view the token at any point, okay? Or you can delete the token also. So once you log in from Hugging Face, you can do that. Okay. Now, once I've given the Hugging Face token, I'm trying to log into this token. All right. And we're going to set up this model, right? So Mistral 7B trained on 7 billion parameters. I'm going to use this model, connect with it. All right. Now, we have entered a test prompt here, which says explain quantum computing in simple steps. And in simple terms, it's generating some response. So my prompt was to explain quantum computing in simple terms. The response it has generated is quantum computing is a type of computing that uses quantum mechanical phenomena such as superposition and entanglement to perform operations on data. In classical computing, data is stored in bits, which can have a value of either 0 or 1. In quantum computing, data is stored in quantum bits or qubits. Okay, it's giving some sort of theory about the quantum bits. Okay, instead of this, let's give another natural prompt. Maybe we'll try something else. I'm going to experiment here and say, explain these steps to make an Italian coffee. Okay, so look at the response that it has generated, right? Making an Italian coffee, also known as espresso, it requires specific equipment and a careful process to achieve the rich, full-bodied flavor that Italians love. Uh, the steps of these are given here below. Gather your tools and ingredients. Espresso machine, manual or automatic, freshly roasted, high quality espresso coffee beans, coffee grinder. It's basically telling you all the tools that you need. And then how do you grind these coffee beans, preparing the port art filter, set up your espresso machine, start the extraction, how do you prepare the coffee, etc. So this is in detailed response. You can also add more parameters here, maybe limit the response to a certain number of tokens by giving certain parameters, max underscore tokens, maybe you can limit to 50, 100, 200, so on and so forth. This is how your LangChain framework works. Let me go back again to the animation itself and elaborate my explanation, right? So what we've done here, we basically at this query instruction stage, the user is providing some natural language question. For example, I have given here a question that explain how to make a Italian coffee, right? Explain the steps that I need to follow in order to make an Italian coffee. It has taken this natural language question that I have asked in English, and LangChain will transform this into a machine understandable query, depending on what is the data source that is coming from. Now, let's say that I did not directly give a prompt like this. Rather, I'm connecting it to a relational database. Then what happens? It will convert the SQL queries into a machine understandable query. This is very helpful if you have some sort of employees data or any sales kind of data and you're asking questions from that particular sales data. Then I can also ask a question in such that where I'm using graph databases for query construction. What happens in this case is it will convert the natural language into cipher queries for querying knowledge graphs or networked data. And then finally, vector databases, which will use self-query retrievers to auto-generate metadata filters and retrieve relevant vector embedded documents via Pinecone vector database or FAISS. Again, that's a very popular vector database, right? Okay, our objective is to convert human language into a format that a specific backend can understand and execute. This is the entire objective of query construction. Then comes your query translation. So even after the query construction, input might not be optimized for the retrieval. So LangChain will provide input rephasing or decomposition techniques like this. What are those decomposition techniques? Multi-query, where you generate different versions of the same query, or decomposition, which will break down complex queries into small parts, like smaller questions. Then comes RAG fusion, which will combine multiple retrieved outputs using fusion methods. Then HYDE, which is hypothetical document embeddings. This will generate synthetic documents in order to retrieve better context. And then step back prompting can also be used. Step back prompting basically will ask a broader question first to guide towards the correct answer, right? So our goal of the entire query translation is to make the question more suitable for the retrieval system in order to get a high quality relevant results. That's the concept of query translation. Then we have routing. Once a well-structured query is formed, okay, at this point, once I have a good structured query, it must be routed to the right knowledge source, right? So we have different types of routing here. Either I can go for logical routing or for semantic routing. Logical routing says that the system chooses either between the sources. It will choose either between relational database or graph database or the vector store, okay? Using heuristics or LLM reasoning. So it will do some sort of reasoning here and choose which database is better to receive the prompt. Or you can do semantic routing, which embeds the question, compares it with the available options. That is, it will look into the previous prompts, probably, and the databases itself using cosine similarity. Cosine similarity is pretty common to us, right? Cosine similarity in order to select the best path, which database that it has to enter. So the goal of routing is to dynamically select the right data source or prompt template in order to get optimal answers out of this. Okay. Then the next step would be indexing. So LangChain will use indexing in order to optimize how the documents are stored and retrieved in the first place. This is a very crucial step for speed and also for getting a very relevant answer. Okay. In this, I have chunk optimization. This will basically split your huge text document into meaningful chunks. Okay. Based on the sentence length or based on some sections, if you have made any paragraphs or any delimiters, full stops, these kind of things that you have used, based on that, it's going to split the entire Word document into some sort of chunks. Then we also have multi-representation indexing. How this works, right? It will store both the original document and it will create summaries of your original document. It will provide multiple ways to retrieve and respond. Then we also have specialized embeddings. What happens in specialized embeddings? This uses domain-specific models like BioBert and Colbert to generate embeddings tailored to the task. Then we have hierarchical clustering, indexing, breaks down the documents into nested summaries, for example, Raptor. This was useful for understanding large or deeply structured content. The entire goal of indexing is to optimize how data is represented in the memory and retrieve for accuracy and efficiency ultimately. Then we have retrieval. Now, what are we doing in the retrieval? LangChain's retriever module will support the intelligence section and ranking of content. So I can use ranking. So we use models like RankGPT or ReRank in order to retrieve documents based on the relevance. Or refinement I can do, that is CRAG, where you're applying post-processing to clean or filter content. Then we have active retrieval, where if initial retrieval is insufficient, then the system will requery using an alternate search or even browse the web, in fact, right? So the entire goal of this retrieval is to ensure only the most relevant and useful documents are passed to the LLM. Most relevant and useful documents according to the prompt that you have initially given. Then in your generation level, finally, once the relevant data is retrieved, the LLM will generate the answer. So there's self-RAG, which is self-retrieval-augmented generation. This will evaluate the quality of generation and uses it to determine if more or better content is needed. Then you have RRR, which is rewriting and re-retrieval. Rewrites the original question or refines the prompt based on generation feedback in order to improve the results. The end goal of generation is it will use the retrieved knowledge in order to produce coherent and insightful answers appropriate for your prompt. So, what are the key benefits of using a LangChain architecture? It is modular, that is, at each stage, it can be customized. So many options we have, right? Next advantage would be data aware. It works with structured, semi-structured, unstructured data. Any kind of data, we can use it. It is context aware, that is, it combines reasoning retrieval and generation in a feedback loop. Then it is scalable because it can be extended with new LLMs, vector stores, or even custom routing logic. Okay. Real world use cases of this LangChain framework would be enterprise chatbots with access to internal knowledge bases, legal research assistants, which will retrieve the legal documents, medical Q&A, where you can, medical Q&A platforms where you're using the clinical literature, and then customer support automation with personalized memory. This is about the LangChain framework. Thank you so much for joining us today. Maybe in the next session on next Wednesday, we'll connect back with a better web framework. We'll explore so many more web frameworks that LLM frameworks that exist, right? Thank you so much for joining in. Thank you.